lecture with actual sound. I will begin. So, dear Father, we thank you for this day. Thank you for the students. Just ask you to bless our work today. Help us to just understand a little bit more about your creation and about differential equations. And we just again thank you, Lord, for your many blessings to us. In your name I pray, Lord Jesus. Amen. Can somebody shut the door back there for me? Thanks. Let's see here if I can find a working marker. So I heard some of you guys talking about Euler's method. Let me just circle back to that and get it out of our system. Because I've mentioned to you what it is, but I haven't really explained to you how to do it, right? And so Euler's method is a numerical method, all right? It is a method for approximating solutions to differential equations. And so let's see if I can work through an example for you guys. I will be lazy and use the one in my notes because that way I won't be punching a calculator like a fiend here. Maybe I shouldn't do that though. Yeah, let me try. Let me try to do something besides the trouble with the notes. The one bad thing about the notes is example 2.11. I have dy dx equals to y, which is an unfortunate choice because that means that the differential equation is the same as one of the coordinates, so it's hard to sort of see the contrast of y and y, if you will. So let me try something a little bit different. Let's try something like dy dx equals to, I don't know, xy. That's sufficiently different. And so we're going to look at that differential equation, and I'll choose the initial point of x naught y naught equal to, I don't know. Let's do 1 minus 1 just to introduce some signs into this. Okay, so let me explain to you graphically what we're doing. All right. So I'm gonna draw like a picture here to kind of try to sort through what's going on. And so we're gonna use Euler's method with, let's say, a step size of 0.2. I'll do it like the notes. And our goal is to estimate y of, let's say, 2. All right. So I'm starting us at x naught equals to 1, right? So our solution maybe is starting right here. This is my initial data point. All right. Then Euler's method says you look at the differential equation, all right, and you draw a tangent line basically through that point. What's the slope of the tangent line? It's given by the differential equation, right? So this right here is the, I think I used big F of xy for this thing. Big F of xy. I thought I had it. But let's see here. So first order of business, what is big F of x naught y naught? Well, it's 1 times minus 1, right? Which is minus 1. So I look at a slope negative 1, right? So I do slope negative 1. That takes me to my second point, right? And this is not quite, I've gone too far. If you don't mind, I'm not going to try to draw it to scale. Well, I will. Okay, I'll attempt a little bit for scale here. That's kind of it. What would that point be? See, that point, you'd have x naught plus h, and so let me just put the numbers in. My bad. So x naught was 1. If I go 0.2 more over, this would be 1.2. All right, and what's the, where is that point? So what's the slope? Minus 1, right? So if I go to 0.2, if I go 0.2 over, I go 0.2 down. So I started at -1. This would be minus 1.2. All right. So let me just. Here you go. Here's the algorithmic form of it. X sub n plus 1 is equal to x sub n plus h, and y sub n plus 1 is equal to y sub n plus f of xn yn times h. But I just want to emphasize to you, all this method is doing is following tangent lines from the initial point plus a little bit. So if you ever forgot this rule for it, you could derive it geometrically pretty easily. Look, so what does this say for our current problem? This says x0 is 1, x1 1.2, x2 1.4, x3 1.5, it's going to be 6, my bad, x4 1.8, and finally x5 2. So once we get to the 5th step, that gives us an approximation that we're interested in for this example, okay? So the x's are easy. You just go, you keep stepping over point, in this case our step size 0.2 each time, okay? The y's are more interesting. So like y1, right, was y0 plus f of x0 y0, which I just explained to you, is minus 1 times h, right, times 0.2, which is minus 1 minus 0.2, so y sub 1 is minus 1.2. What's y sub 2? It would be y sub 1, which is minus 1.2, right? Plus, what is my f of xy? So now I'm supposed to do f of x1. I'm supposed to do f of x1, y1. What would that be? X1 was 1.2. Y1 was minus 1.2. And my h, still 0.2. Right? So that is 1.44 times 0.2, which is time to get a calculator. Otherwise, I'm going to make an error, and then you guys will tell me three minutes later, and then I'll regret my life. Let's see here, 1.2 squared times 0.2. It's all negative, so plus. So I get minus 1.488. How do you find y3? y3 is y2 plus f of x2 y2 times h, right? In our current context, that is minus 1.488 plus minus plus 1. What's x2 is what? 1.4. So 1.4 times minus 1.488 times 0.2. All right. So we do the math. Again, it's going to keep going negative, isn't it? I get 1.904 minus 1.90464. That's my y3. So y4 is minus 1.90464 plus, what's my x4 was my x3. Notice that notice that the algorithm it links n plus 1 to n. So when you're calculating the n plus 1th one, you got to use the nth data point. So I'm on y4. That means I need to use x3 and y3 to figure out the slope, because the slope of your approximation is always kind of governed by the previous one, right? So this is kind of doing something like this. Anyway. All right, so what was I? 1.6 times minus 1.90464. Now, do you need to keep all these numbers? I mean, it depends on my homework instruction. I think usually maybe 3 decimals will suffice for our purposes. We're not too serious about all this, yeah? Now, if I was teaching a numerical methods class, then that's really bad, because that means that Dr. Wang is not well. Let's see here, times 1.6 because I shouldn't teach numerical methods. Dr. Wang is the expert here. If you have questions about numerical methods, you go ask him. Just be prepared to listen to a 30-minute talk about Julia, because he loves Julia. Did I mention he loves Julia? Let's see here, 2.51 minus 2.514. I'm just going to keep that many digits if that's okay with you guys. What's that?
We asked who was Julia.
Oh, Julia, it's this new computer program. So, language. Let's see here. It's relatively recent, maybe last decade or so. So let's see here. Then minus 2.514 plus my x4, which was 1.8. All right, times my previous y, which was minus 2.514, times my step size, which is 0.2. And what's that give me? Approximately minus 3.4, probably 3.419 is good enough. There we go. All right, so thus y of 2 is approximately equal to minus 3.419. That's what Euler's method gives us. And again, graphically what you're doing is you're just tracing out the direction field, really. You're implementing that connect the dots with following the tangent lines at the level of actually plugging in numbers into the differential equation to generate the slope for the approximating line segments. That's what Euler's method is. Yeah?
Wouldn't we have to do another iteration of that to find y2?
Nope, because y5 is paired with x5. Now, suppose you want to do better, right? I don't know how many of you voted for Biden. If you voted for Biden, you're probably going to tell me to do better. But wait a minute, are you old enough to vote? Don't tell me. That's all right. Whenever I see somebody say "do better" online, it just makes me go, "Just shut up!" Like that phrase, "do better." It's just, are you my mom? Like, just shut up, dude. Anyway, so example 2. Let's just solve this thing, yeah? dy dx equals to xy. Because we can do better than Euler's method. Sorry, I said it. Because I'm pretty sure this one we can separate and integrate, yeah? So this gives me dy over y equals to x dx, yeah? Let's take our initial condition method for a spin, right? So I want to find the initial. I'm interested in what point? My initial point is 1 minus 1. I want 1 minus 1 on my solution curve, right? You know, y of minus 1 equal to 1. So it's useful then to integrate this basically from, let's say, y naught to y1. Integrate this from x naught to x1. I'll just leave it symbolic for a second. If I do that, then I've got natural log the absolute value of y1 minus the natural log the absolute value of y naught equals 1/2 x1 squared minus x naught squared. No need to add a constant here because I'm doing definite integrals, right? And okay, then what? This gives me natural log of the quotient of, let's say, y over y naught equals, 1/2 x squared minus x naught squared. Here I'm setting x1 equals to x. Now the reason, why didn't I just integrate to x and integrate to y to start with? It's just a mathematical, what's the word? Sort of mathematical table manners, if you will. I mean, so it's just not done to put the same variable here and here. See, the y and the x inside the integration, this is the dummy variable of integration. If your bound, right, is the same letter as that, it begs the question of, which one is which? It's a question of propriety. I guess. So to avoid this mathematical, using the wrong fork, if you will, I just put an x1 and a y1 there. And in physics, you'll see people swap out the integration with tau instead of t to avoid this issue. Like technically speaking, you really should never be writing something like g of t dt and then putting a t up here. So to avoid that incorrectness, sometimes people do something like this. My current approach is just to put a number on the integration bound instead, okay? Just so you know what I'm doing. All right, so that's just a comment. Now we can solve for y. What do we got? Y is equal to y naught times e to the 1/2 x squared minus x naught squared, which in our case is y is equal to minus e to the 1/2 x squared minus 1. So there is the explicit solution to the initial value problem. And we can see how we did, right? How did we do? We can compare the exact result with the approximation and see how we fared, right? So what is y of 1? What did we get? Excuse me, 1? This is supposed to be 2, right? So y of 2, what do you got? Minus e to the 1/2, what? 4 minus 1. So we got what? Minus e to the, apparently, 3/2. What's that equal to? I have no earthly idea, but I could figure it out with a calculator. I mean, you could figure that out without a calculator, actually, by the end of this course. But at the moment, we'll use a calculator. I get minus 4.482. There you go. So as you can see, we didn't do too well. I mean, it depends on how you want to look at it. This is easily understood, though. This makes sense why this should be less than the actual value Euler's method gave us. Can you explain to me why? Why was Euler's estimate an underestimate of how negative it is? Yeah.
Maybe because the step wasn't
You're blaming it on the step. I agree. That's definitely part of it. So like, let me just kind of picture what we did. We did like this, right? Then like this, then like this, then like this, right? Something like that. That's a roughly picture of it. But what's happening to the slope, actually, as you think about it, the slope is xy, right? So as you're drifting down here, the slope is actually worse than your starting point, right? Like the slope was -1 at the top, but by the time we get to the bottom of the line segment, it was -1.4. But actually, in the middle of the line segment, it was like -1.2. And so if we had chose a smaller step size, we would have drifted down further, faster. And that's why we have actually a larger negative number than we got. It's just that. If we increase the step size, and I am not going to spend all of class time increasing the step size, we could do better. Oh. Sorry, whenever I say that, I just feel wrong. Anyway, any questions? That's Euler's method. I never test on this in the test. Yeah.
X naught was defined by the y negative 1 equals 1, right? X naught is the negative 1.
Yeah, x naught is the starting. No. X naught is the 1. X naught's equal to 1. Y was the initial y position. So if I had instead put, if I'd put y equals to 2, we would have started up here, and we would have drifted upwards. So.
What do you use the notation of y negative 1 equals 1?
Use which notation? Sorry.
You said dy dx equals xy with y. You put in this negative 1.
Oh, like this notation here?
No, above that.
Top right.
Right there.
Oh, that just is the function notation. We're looking for y as a function of x. So we're plugging y as y of -1.
Wouldn't that make your x?
Oh my goodness, yeah, I meant to put, my bad. What should I put here?
That should be Eulers.
Oh, yeah. Sorry. Your question is a good one. The answer is, I don't know why I did that. I think what I meant to put here is y of 1 is -1. There we go. So sorry. Thank you. Excellent question. I should start to treat you like my one of my professors. I had a class with my wife once, and she'd be like, anytime she's frowning, the professor would be like, "All right, what's wrong?" All right. So anyway, let's move on here. So that's why I didn't try to do this the other day, because if I'd spent all this time the other day, it would have like completely overemphasized this material and given you the wrong impression of the importance of Euler's method in the larger story of what we're doing. I want you to see it's something you can do. This is one of like the foundational numerical methods. This is at the heart of most of about half of the numerical methods are based on this idea. So it's an important thing to see. The fact that we're iterating, that the n plus 1th step is based on the nth step, this is a very important idea. All right, so most numerical methods in mathematics are based on this kind of iteration. All right, so that's an important thing to see. We'll be doing a lot more iteration as we go into the next story arc in the course, so we'll get there. Oh, okay, so back to substitutions then. Back to substitutions. And our next is a substitution that is named after a famous family of mathematicians, the Bernoullis. So I'll just attack it and we'll see how it goes. I think if I remember right, this one's got kind of a perhaps non-obvious substitution. So this one will, let's just take it for what it is and see how it goes. Example 3. Let's see here. This is my example 5.5 if you're keeping track on page 13 of the first order. So we're supposed to solve y prime plus xy equals to xy cubed. We're going to call this star. All right. So so here we take the somewhat novel step of multiplying by dividing by y cubed. All right. So I'm going to rewrite this as y to the minus 3. And I'm going to put the y prime as dy dx so you can see it better. Plus what? X y to the minus 2 equals to x. Okay, so I just divided by y cubed, basically. And you might say, well, why are you doing that? I guess the reason you're doing that is to make it look more like the integrating factor method problem, right? And that's still kind of a stretch, but you do that. And then what you can do is let z equal to y to the minus 2. All right? And if we do that, what happens? dz dx is what? Minus 2 y to the minus 3, right? dy dx. And then, if you look at this, see what this says? This says that y to the minus 3 times dy dx is actually equal to what? It's actually equal to minus 1 over 2 times dz dx, right? So if you look at that, that means, well, that's what we have up here, right? See that? This and this match. Which means I can trade out this y to the minus 3 dy dx for a minus 1/2 dz dx, right? And what would xy to the minus 2 be? xz, right? So plus xz equals to x. And now we're almost to a linear differential equation in x and z, which we learned how to solve yesterday in the letter y rather than the letter z, but so let's multiply by minus 2. What's this give us? This gives us dz dx minus 2xz equals to minus 2x. So recognize at this point, this is an integrating factor method problem. What should I make my integrating factor for this one? Exponential integral of minus 2x dx, yeah? So identify that the p here is the coefficient of z, which is minus 2x. Now that we can integrate, it gives us minus 1/2, it gives me minus x squared, right? So apparently, e to the minus x squared, an interesting function, right, is the integrating factor here. Let's see if it works. Multiply by the integrating factor, what happens? We must multiply by the integrating factor and see where it takes us. So we have e to the minus x squared times dz dx minus 2x e to the minus x squared times z is equal to minus 2x e to the minus x squared. All right? Now what do we do? The step that has confounded many of you yesterday and will probably still confound you today. The reverse product rule, right? And so this is d dx of what? It should be the integrating factor times z. Is it logically? Does that actually work out? If you differentiate e to the minus x squared times z, do you in fact get back to what we had just above? Do you? Try it out, right? We get dz dx times the exponential plus z times the derivative of the exponential, but that exponential has an inside function, so by the chain rule we get minus 2x e to the minus x squared. And there you have it. Well, we're not done yet, of course, but this is all equal to minus 2x e to the minus x squared, which is gloriously integrable by a u substitution, right? Let u equal what? Minus x squared. If you let u equals minus x squared, you can integrate that. It's just minus 1/2. Wait a minute. No, it's just e to the u. So this integrates to e to the minus x squared times z equals to e to the minus x squared plus a constant, actually. Integrating both sides. Now try it out. If I differentiate the right-hand side there, do you get back what we started with? Try it. Differentiate e to the minus x squared. What do we get? We get minus 2x e to the minus x squared, right? So that means my integration on this side is legit, right? If I differentiate this and I get back to that, I integrated correctly. So I did. And here, we're integrating the derivative, so hopefully you can't mess that up, right? So that one's, I can't mess that up, I should say. And now what? Yeah, now we have to go back to y, right? So z, I'll put it up here. So what we have is we've got, I'm going to isolate the z. Z equals to 1 over y squared, right? And that's equal to, solving for z here, 1 plus c e to the x squared. Do you guys see what I did? So I took this equation, I multiplied it by the integrating factor. Well, I divided by the integrating factor to be more correct, right? So multiply by e to the x squared. That cancels out this one and leaves me with a constant times e to the x squared. And that's all equal to z. Z is 1 over y squared, so we have this. So lo and behold, we have y squared, 1 over 1 plus c e to the x squared, which gives me y is equal to 1 over, well, plus or minus 1 over the square root of 1 plus c e to the x squared. If you want the explicit general solution, there it is. So this is an example of a Bernoulli. This is a Bernoulli differential equation. There's a whole family of ones that are very similar to this that allow a similar substitution. I have a box. If you look at my page 14, I give you a remark that gives you like the general rundown on, you can do this for any one, like the pattern here. Anytime you have dy dx, I've already forgotten it. Should never put money on a game of memory. Because it's wrong to gamble. Let's see here. No. Let's see here plus. Let's see here. P of x. So if you have anything like this, P of x times y equals to Q of x, y to the n, right? So anything of this form, this is generally a Bernoulli. This is Bernoulli type. So this was Bernoulli with n equals to 3. Yeah? So if that's the pattern, if this is the pattern of your differential equation, basically you can make a z equal to y to the minus n plus 1 substitution. That's the secret sauce for these ones. If you make that substitution, it will take the given nonlinear differential equation and convert it into a corresponding linear problem in z, which is pretty snazzy. Any questions? Yeah.
So what did you do when you was manipulating dz dx? What it equal to dy dx?
Oh, so I started by making the substitution right here, which admittedly is unmotivated and from the thin blue air. All right, but to come to an understanding of where that comes from, you just have to sit and fiddle with the differential equation for a couple hours. Something like that. I don't know. It depends on your creative spark, right? Like how long does it take you to see it? I don't know. Some of us never. Me never, maybe. Put money on the line, maybe. Put me on desert island. Make it the key to killing a horde of robot monkeys or something. I don't know, but so somehow you have to have the creative spark to see that. Then I differentiate it to understand the differential relation between the new variable and the old variable. And so that's what I did. I differentiated z. And then when I make substitutions, I try to make my life easy. So I look to take what I have and rewrite it in terms of what I'm already facing. I'm already facing y to the minus 3 dy dx. That is why I do algebra here to solve. I say, oh, wait a minute. I already have that. Let's solve for that. So I solve for that, and that allows me to replace the dy dx term times y to the minus 3 with a simple minus 1/2 dz dx. And then that gets us to the red step, at which point I'm like, well, this still isn't quite the right format, right? The format we learned to solve last time was linear differential equation, which has to have the derivative of the dependent variable on its lonesome at the start. It has to be like y prime plus py equals to q. In this case, z prime plus pz equals to q. So that, and then that's the story.
Yes, sir. Thank you.
Yeah. Now, so there is no end to these substitution stories, all right? If you take a class, I know there's some kind of in each particular subdiscipline of science and engineering, there are substitutions which are native to certain problems there that you won't see unless you take that major. There are just intricate, interesting substitutions that arise from particular applied problems. But I want to show you one other